Point of this, but what am I showing you here? What did this show yesterday? What is it? Chromatography, right? The red one, okay? This is for our friends Kiki and Skylar. The red one has just one part, okay? One phase, it's all red. The blue one here, it's like purplish and blue. You could argue it has two phases, but I'm still gonna say that's just one. It's a different kind of shade of blue. So blue really doesn't really have a whole lot of different parts, but the black one here, has multiple colors. I see yellow, orange, red, purple, and blue. So the black one has more phases. So you could argue with me and say this is heterogeneous, but I would argue it isn't. Okay, just like the marker on the board, it looks uniform, right? So all three of these I would say are homogeneous, but chromatography can be used to separate components, right? The water goes up and it separates based on forces of attraction. All right, so just be aware of what chromatography is. Another way to separate mixtures, okay? It's another way. All right, so today I want to talk about those two phrases there, conservation of mass, conservation of energy, how it applies to physical processes and chemical processes. But one thing I just wanted to real quick make sure you guys are on board with. For a chemical reaction, okay, so yesterday I wrote down H2O breaks down into H2 plus O2, right? Didn't we just write that for electrolysis? That was the last thing we wrote, I believe, okay? So again, electrolysis is when you send electricity through water and it splits, right? So this is a compound, you're chemically changing it by sending electricity through it. You're making hydrogen gas and oxygen gas. All right, I just want to make sure you understand how to read this. What's this called? In a chemical reaction, what's this called? The starting material in a reaction. What do we call that? Reactants, right? So here's our reactant. What's that mean? What's that arrow mean? Starts with a Y or a P? Or an F? Say it again? Close. Let's use the Y word. Yields, right, so that arrow means yields, okay? That's yields. So this reactant yields, what do you call what you create? Products. These are called products. I just want to make sure you guys are on board with that you understand how to read a reaction. Reactants are on the left. The arrow means produce, it means form, it means yield, and then these are your products, right? You're producing products. So products are always new substances, different properties than your beginning. All right, reactants, okay? So it changes chemically. So again, electrolysis, this was an example. I will show you that. All right, it's how you separate compounds, not mixtures, because it's a chemical change. All right, but it's part of the whole separation conversation. All right, so I'm gonna move on now. Conservation, let's do of energy first. Conservation of energy, and that's what this this packet is all about here, okay? So, Skylar and Kiki, you're gonna miss this, but I can show you when you get back. Okay, first of all, who can read their, actually, you know what, don't read your definition. Hold on. Okay, so now, everybody felt this yesterday? Steve didn't. Go ahead, Steve. Okay, too touchy there. All right. Did you guys think it was cold, warm, room temp? Room temp, okay? All right, now, I'm gonna take this little coin and observe. So you're gonna watch what happens, then you're going to feel it again. Then you're going to write down, underneath this, you're gonna write down your observations and how this teaches you the law of conservation of energy. Yes, sir?
I was not going to feel that.
Oh, I'm sorry, Ben, you weren't here yesterday?
I left.
Oh, so you were here and then you left like halfway through or something?
Yeah.
Yeah, sorry, Ben. It's important that you feel it first. Okay, you with me now? Okay. All right, so I'm going to not break, but bend this little coin, whatever you want to call it. Something's going to happen. You're not saying anything. You're writing down your observations, and then I'm going to have you feel it. And then I'm going to have you write down how it applies to the law of conservation of energy. Okay, here we go.
forever.
Okay, write your observations down. Okay. Write down your observations, and I want you, if you looked up this definition like you were supposed to, alright, oh sorry. So should I ruin it for them? Should I show them? Alright, you guys have to come back to school to see it. So, but I am going to talk about it. Oh, that's right. Anyways, write down how this applies to this law. So you should have looked up the definition. And so now trying to apply it, right? So looking up a definition doesn't really mean you understand it. So now you have an example. This is a great example of this law. I mean, everywhere you go in your day. So from here to where the rest of the day, this is all over the place. Everything you experience is this. But this is a great example because you're directly in contact with it. So observation, how it relates to the law of conservation of energy. And I'm going to throw one more thing at you. There's two types of processes in the world that involve energy. One process releases energy, the other one absorbs energy. That's really all there is. Either something is giving off energy or something's absorbing energy. This is one of those processes. I think you probably understand which one, but there's a name for that. See if you can think of that name. What is the name for the process of releasing heat, or the name for the process of absorbing heat? There's names for those. One word that describes those processes. We're going to talk about that too. Okay. So observations, how this applies to the law of conservation of energy, and what's it called? What's that type of reaction called? All right, that should have been enough time. Who knows the definition of the law of conservation of energy? Okay, I didn't write law, I don't know why. The law of conservation of energy. Sorry. Who's got the definition? Who looked it up? Taylor? What do you got?
States that energy is not created or destroyed, but changes forms.
Energy is not created. You should already have this down, so you don't really need to. Yeah, it looked as if it was off a little. Thanks, Amy.
Yeah.
Energy is not created or destroyed. Only what?
Changes forms.
Yeah, can I alter that a little? Yeah, I'm a teacher, right? I can do whatever I want. Okay. Just checking with you, it's your definition. Energy is not created or destroyed, only transferred. Every year I have the same problem. Is there 2 hours or 1 hour in transfer? Why do I think 2? I throw 2 letters in all the time. Be a better speller than me. There are 2?
In transfer.
It just looks weird. You know, ultimately it doesn't matter to me, but you guys should have, you know, better grammar and spelling than me. You know why I'm not a very good speller, Jake?
Why?
I don't read a lot. People who read a lot have good vocabularies, they can spell very well.
Yeah.
So take my advice, read more than me, which means read something once in a while. I get some like news briefings in the morning, email and apps and stuff, so I'll read like short blurbs about the news, but you know, that's about it. Anyways, energy not created or destroyed, only transferred, and we'll leave it at that. And actually, what'd you say? There's different forms? Transferred, and we'll add that. Different forms of energy, different forms. We're going to talk about that a little bit, okay? All right. So energy is not created or destroyed, only transferred. So now, you guys wrote observations. Someone volunteer. What'd you write? What was an observation? Jake.
I just wrote exothermic reaction.
Good. Well, give me an observation. No, that's not an observation. Did you write any observation stuff? I needed to not, someone tell me what you wrote. Give me an observation from feeling it or looking at it. Got cloudy and hot. Very good. Yeah. Anyone say it turned white? Okay. You know what? I'm gonna cut to the chase with this immediately here. This was a physical change. It's not chemical. Why is that confusing? It gave off heat and it changed color. Okay. I will explain that, but first let me get some other things down, okay? So this was a physical change, and all I have to do to reverse this is put it in boiling water for like 10 minutes, and all the white stuff will go away. Take it out of the boiling water, put it on a table at room temp, let it cool down, it'll be just like it started. So that's kind of evidence that it's physical. I can't just take a compound, warm it up, and it goes back into its elements. That's not gonna work, okay? So physically, right, I can heat it up. That's a physical change. So anyways, what you said is good. It gave off heat, it turned cloudy. So it gave off heat. It is exothermic. Let's write that down. Exothermic process. Now, exothermic can apply to chemical and physical. You ever get embarrassed? You ever feel embarrassed in your life? Sure you have, okay? Everybody does. When I get embarrassed, I tend to get hot, I get warm. Anyone else? And I get flushed and I may start to sweat, okay? That's a chemical change. There's chemicals in your body that's creating that heat, okay? It's not a physical change. Anytime you get hot from a feeling, that's chemical, okay? Your brain's telling your body, you know, almost like going into like, what's that phrase? Fight or flight mode. So your body's like getting revved up because you're feeling embarrassed, like, oh, am I gonna stay in this or am I gonna run away? Like instinctually, that's what your body's thinking. So anyways, I'm just trying to give you a fairly common example of that's like a chemical change of heating. This example, exothermic, is physical, and I know that's confusing. I'll explain that. All this means is releasing heat. So if we feel something that is hot, it is giving us heat. Would you agree? So touching this heat is going into my hand and my brain's going, ooh, that's hot. Make sense? So this is releasing heat. So if we feel something that's hot, it's exothermic. Okay, releasing heat. I'm gonna put that in parentheses. Feels hot to us. Now the book gets into some details here with surroundings and system. The system here is releasing heat to the surroundings. So the air is also gaining energy from this. So this, when I say exothermic, it's from the perspective of the system, the reaction, the change. So this is giving heat. The air, us, the table is all taking in heat, right? So I just want to make sure you understand that. Okay, releasing heat. Okay. What's the other process? Endothermic. I'm going to show you that tomorrow. Okay, I didn't have time to get anything ready today. Well, I mean, I did have time to be honest, but I forgot to get that ready. Sorry. Endothermic process is the opposite. It's absorbing heat. Absorbing heat. And that feels cold to us. Who thought that was going to be cold? Yeah, for some reason that's common. If that was a cold pack, if it got cold, so imagine this was really cold, our heat would be going into it. That's why it feels cold. It's absorbing. This would be absorbing if it was cold, but it's not. That's why it's the exothermic. So when I put my hand on the desk, it feels cold. The desk is absorbing my heat. So anytime heat is absorbed, that's endothermic. Okay? So Taylor read the definition. Energy is not created or destroyed, it's only transferred, and it's in different forms. Okay, so we'll talk about that in a second. But these three are really important to remember all year. Okay, but specifically, our next quiz you'll have questions on this. So releasing heat, exothermic, absorbing heat, endothermic, and this is the result of this. Energy is always being transferred constantly. Okay, you are warmer than the air at all times. You are always putting energy into the air. Energy is transferring from you to the air, or to whatever you come in contact with. Okay? Infrared, what's that? You ever hear like infrared goggles or something like that? Anyone ever heard of that? Okay? If you were to look through infrared goggles, we would all be red, like glowing red, because we're giving off heat. In the room would be not as red or blue. Blue means cold. So the point is, energy is always being transferred. Now, let's talk about the different forms. We got to talk about how this proves this. How does energy move? Raise your hands. How does energy, we'll put heat, right? We talk about heat mostly, and I'll kind of explain what that is, like what is thermal energy, what is heat. Okay, how does energy or heat move? Raise your hands. Ben?
Radiation.
Okay, radiation, explain that.
It transfers through the air.
It can, but it could also transfer through like metal, right? Metal conducts heat. Good, you're good. You're not wrong. That's right. But I'm looking for something. How do you know? Why does it move at all? That's a better. Actually, I should have wrote. Why does energy move? That's a better question, not how, because that's right. But why does it move? Want to elaborate?
It goes from high concentration to low concentration.
Yes, very good. But give me a different word than concentration. You're not wrong. Energy. How does energy move? It moves from high. Someone help me out. Why do you glow red on the infrared goggles? But the air is like bluish, maybe. Or green, it's kind of in the middle.
You're hotter than the air.
Yes, you're hotter, so you have a higher temperature. From high temperature to low temperature. So when that, oh wait, I'm going to give that away. So how does the hot pack demonstrate the law of conservation of energy? This energy isn't lost. It's just transferred from where to where, Liam? What has more energy, me or the hot pack? Hot pack. How do you know? It's hotter, higher temp. So how does this demonstrate the law of conservation of energy? The energy is transferring from. Well, this has more energy than me. You agree? Because it's warmer. So if I'm holding something that's warmer and you read that, how is the energy moving? From me to the hot pack, or from the hot pack to me? Very good. Energy always moves from higher concentration, that's fine. That means higher temperature to lower temperature. So a hot pack, oops, forgot the word pack. A hot pack transfers, that's only one arm, transfers energy to your hand, for example. So hot to cold, high temp to low temp. I feel like there was a teacher over this, not the summer, but the end of last year, I was grading the Regents exams with her, and she tells her kids this little phrase, hot to not. I like it. Hot to not. Energy moves from hot to where it's not hot. Hot to not. I thought that was cool. So I'm giving her props for that, Miss Gregory. So high temp to low temp, hot to not. So hot pack is hotter than us, so it goes into our hand. That, just holding this demonstrates conservation of energy, okay? That's what the law is all about. The energy doesn't just disappear, it goes somewhere. Even if it's to the air, it's going somewhere. Okay. Thermal energy, also known as heat. Thermal energy / heat. What causes it? I'm just going to give it to you. Caused by particle motion. The faster particles move, the hotter they get. That's why if you were to get up and run around the room 30 times, you would get hot, maybe start sweating, because your body is moving and the particles in your body, your heart's pumping faster, blood's moving, everything's moving faster, so you get warm. Thermal energy or heat energy caused by particle motion, okay? Caused by particle motion, all right? If you're hot, stop moving. You ever hear anybody say, you know, if you're really hot and you're kind of doing this, I remember when I was in school, teachers used to love to tell me this, and I just kind of wanted them to just say, I just wanted to tell them, shut up, be honest with you. So you anyone do this, and the teacher says, you know, you're spending more energy doing that, so you're actually getting hotter. Has anyone ever told you that? That's really one of those annoying things to say to somebody, because maybe it's true, but the wind feels good. So it is true, but it's annoying. Caused by particle motion. So when you're moving, you're increasing your temperature. All right. So this was all kind of the, I guess, short version of the conservation of energy. There's more we could go into, but we'll wait and go into it down the road. So what do you need to know today? What is exothermic? What is endothermic? How does energy move? All right. What is thermal energy? Okay. And how does that all apply to the law of conservation of energy? Questions? Okay. Next. Your homework is not on any of that. Your homework is on the other one. Law of conservation of mass. All right. Law of conservation of mass. Okay. So let me make sure I am covering everything I wanted to. Okay, all right, so here's what I'm going to do. I'm going to show you a reaction, but you're going to sit here and stare at the screen here because I'm going to get fancy and use Apple TV. So this is very simple example, but it gets the job done. And the scale, it didn't work out perfectly, but usually it does. Sometimes when you kind of push on the scale or whatever, it'll kind of even out and it'll be off a little bit. So law of conservation of mass, you're writing down why I showed you that. What does it have to do with the law of conservation of mass? I'll write the reaction. Here it is. It was KiAQ. That was in the flask. And then in the pipette was AgNO3AQ. So those are my two reactants. Then I drop the, squeeze the pipette, and I drop this into the Ki, and what happens actually is the Ag and the K switch spots, and you get Ki and Ag, or no. Jeez, losing my mind. KNO3 and AgI. That greenish, white, solid, cloudy stuff you saw is the silver iodide. The KNO3 is still in there, aqueous, dissolved. So that precipitate, we call it, this is called a PPT. You can write that down. PPT. That solid is evidence it was a chemical change because I started with two clear solutions, colorless, and I got a cloudy precipitate. What was the mass before I added 112.1, right? So before, with just the reactants, it was 112.1. After it reacted, it was 112.0, but it should have been 0.1. Okay, it was off by a little tiny bit. Raise your hand. What am I getting you to write here? We're going to stop after this. Ben?
The chemical change didn't change the mass.
Good. Chemical change did not change the mass. That's what this law states. Mass cannot be created or destroyed. It's only transferred. Eyes up here. 112.1 is distributed among the reactants and the glass and all that stuff. Well, when it reacts, nothing changes. Everything still has the same mass. It's just transferred to different compounds. So the mass of I stays the same whether it's with K or with Ag. That doesn't change. So the particles in the reaction, they don't change as far as their mass is concerned. The properties change, different compounds are formed, but the mass stays constant. That's what that means. Okay, mass will not change, it's transferred, just like energy. Different from energy. Energy is like hot, cold, right? Mass is more of like how much matter you have, but it's the same concept. It's never created nor destroyed, it's just transferred, okay? So from reactants to products. Your book work is talking about conservation of mass. That's the gist of it. There's more to go into, so you might need to look up some things in the book, but that's all right, okay? I'm gonna stop there, bell's gonna ring. All right, good job today. I know it was a lot of notes, but